Okay, I think we can start. It's time. I think it's a good thing to do that, keeping on time. So, good morning or good afternoon, everyone who is listening to me today. This is Cherry Kubota, the Ohio State University Horticulture Crop Science. Welcome to Indoor Ag Science Cafe, February monthly cafe. If you are new to this cafe, sorry. There is a mute button for the lower left you can control. I like to do a discussion time after the presentation, and then you're welcome to use your microphone rather than chat area so that it's more dynamic conversation. And since it's recording, you may be asked to accept the recording status. If you feel uncomfortable, just say no. But if you feel comfortable, just go ahead and say yes. That's basically I think the little video window showing your name and face. I just wanted to go through the usual stuff. So we have a special website to enter your questions. And this question site called Indoor Ag Science Queries. And then it's always open. And then you can ask any questions. And then we gather those questions periodically and then have some time to answer those questions. So that's the function of that. And then my email of Ag Science Cafe email usually have that link just for this. So you can use that. So conference information, we have listed things here, just going quickly. There's a HVAC conference in California by Dr. Greenhouse. In March, we have NCERA 101, Controlled Environment Technology and Use. Group meeting, or actually this is an international meeting this year, Tucson, Arizona. And then June, ISHS symposium, Light in Horticulture. This is a great one, international one, to talk about more science. It's in Sweden this year. In July, we have a plant empowerment workshop. This is more for not educated, how do I say, experienced growers to learn advanced strategies to control environment in greenhouse mainly, but it can be applicable to indoor condition also. And then July, we have a Cultivate event, and then July 29th, which is our project related stakeholder meeting. So this is going to be the first stakeholder meeting, and then it will be Michigan State University, East Lansing. So, and then upcoming cafe series today is going to be by Dr. Paul Fisher, University of Florida, and March Cafe is going to be by Paul Lightfoot, Bright Farms. He's going to talk about food safety in controlled environment. And then April Cafe is going to be Michigan State, Dr. Roberto Lopez, and then soon to be Dr. Kelly Walters, or maybe she's already doctor. But anyhow, so those people going to talk about flavor of the produce and how they are associating with the light intensity. And then the last one I have in the schedule is May Cafe, and then this is going to be by Nicola Koslake. She's going to talk more about financing indoor farms. So that's the lineup. And then today, we're going to have Paul Fisher talking about managing water quality and biofilm in indoor production. And this part is going to be recorded. And then after that, you have a free discussion time. So you don't have to worry about recording. So you can ask basically anything during that time. So with that, I want to stop my sharing here and then wanted to provide the All right.
All right, we're good to go there, Cherry?
Yes. So Dr. Paul Fisher is a professor and extension specialist at the Department of Horticulture, Department of Environmental Horticulture at University of Florida. So really good to have you, Paul. Thank you.
Well, thank you very much, Cherry. It's really nice to be invited and to reconnect with my colleagues on this program. And so I'm going to talk about water quality and biofilm aspects, and we're going to go through some different aspects of water sources and some issues around that, and then managing biofilm within your system. I do most of my work with greenhouses and plant nurseries, a lot on the root zone management, being water, fertilizer, and substrates. The area of indoor research that we're mostly focusing on in my lab group and also with Dr. Selena Gomez is on indoor plant propagation. And in those environments where we've got high humidity and short crop cycles, we certainly see that we're creating a wonderful environment for algae growth and potentially biofilm in our irrigation systems. So we've had certainly firsthand experience with some of the issues that come up from an indoor plant environment. What I'm going to talk about today is going to go through the incoming water sources. I'm going to focus on well and municipal water sources, which are most common for an indoor production system. We're going to talk about, there's so many different water quality issues that you can run into, but we'll talk about just sodium chloride here, chlorine level, and bacteria. And the bottom line is you need to know what's coming in your water source and then treat for the specific issues that you see. And I'll get on my soapbox here. I do a lot on recirculating nutrient solutions, and we teach some online extension courses, and I've been a little shocked to hear about how often indoor growers are dumping their nutrient solution. And I think if we're a bit smart about the way we manage nutrients, then we can reduce our environmental impact and waste there. Then we'll go into biofilm, just briefly what it is and why we should care. And it's worth looking at your entire system to think about where inoculum is coming in, whether it's bacteria, algae spores, or it's plant pathogens or food safety pathogens. And then we'll go into some management aspects. And my bottom line here is that there aren't very many chemical applications that we can make on a continual basis that we're always going to be on the edge of phytotoxicity if we've got a chemical running through our system. So we really want to rely on shock treatments of sanitation, cleaning, and disinfection, and then point treatments that don't have a harmful residual. So let's get started and talk about the main two water sources that we're likely to run into as our source for indoor propagation and plant production. And that's most likely going to be a town supply or municipal supply water, which is treated already to the level of drinking water supplies, or else you have your own well. And so in both of those situations, it's unlikely that we have our water source being the source of food safety pathogens. It's possible. Even less likely that it's going to have any plant pathogens, but the most common risks that we're going to have in both these sources are going to be salts, dissolved ions in the water. Could be, I'll talk about sodium and chloride, but it could be other ions such as fluoride or boron, and so on. It could be an issue. Alkalinity, dissolved lime in your water. And also chlorine, which is being treated water from municipal town supply, can cause phytotoxicity in our crops. Sometimes we'll run into bacteria issues. It could even happen from municipal supply, but usually it'll come in from well water more likely, and then particles with screen filtration. So let's go through those, and let's start with salts. And I'm just going to talk about sodium and chloride here, but as I say, there are many different dissolved ions that can be important. Table salt is sodium chloride. And we get high salinity, especially if we are in a location with that's close to the coast, as we are here in Florida. and we have saltwater aquifers. And so we get high sodium and chloride in our irrigation water. And the main effect of that sodium and chloride is to raise the electrical conductivity, or EC, and the total dissolved ions in our water. And that can have a number of impacts. It can decrease nutrient uptake. So for example, we have high sodium, we're more likely to run into tip burn issues, as we can see on the lettuce in the bottom right here on your screen. And as we're starting to get levels of sodium and chloride that are up at the same kinds of concentrations that we have with our fertilizer ions, such as nitrogen, phosphorus, potassium, calcium, magnesium, now we start to have reduced plant uptake. We also can have reduced water uptake, reduced yield, and poor root health, root burn from these salts. And I'm going to just simplify this down to the idea of salt levels in our water being like a bank account. Our EC level over time is going to change. And if we think about our bank account, we open our bank account at the start of a crop season, and that is dependent on the nutrient solution that we have in our reservoir, which is a combination of the fertilizer and the dissolved ions from our irrigation water. And if we're growing in containers, then there could also be some ions from our substrate. And then over time, as we go through our crop, we're depositing ions into that bank account. And so that could be coming from our water source, and it could also be coming from our initial nutrients and our makeup nutrient formula that we're adding. And we have some withdrawals from our bank account, and the most important one that we're trying to manage is our withdrawal from uptake by the plant, but we can also be discharging some proportion of our recirculated solution into the environment, or we could be leaching it out of our containers substrate. And specifically on containers as well, we get a particular phenomenon where we get a salt layer at the top of the substrate as well, as another withdrawal away from the root zone. So if we're managing high sodium and chloride in our water, then the first thing is that we need to know more than just the EC of our irrigation water. We need to have a regular laboratory analysis of sodium, chloride, and the other specific ions. The nutrient solution that we put into our reservoir and a recirculating indoor production system is going to be a combination of the ions in the water as well as the fertilizer ions. And this is one of the biggest differences from one location to another, is going to be this water quality. So you need to know what it is, and you need to test for it, and beyond just EC. High levels of these ions, we're quite sensitive to it in a recirculating hydroponic solution, because the plant will tend to take up more of other ions, leaving some of these junk ions of sodium and chloride in the solution over time, and those levels build up. So if we're up above 50 parts per million of sodium or chloride, which here in Florida is very common, then that's an issue for indoor production. So we want to be monitoring the EC level in our recirculating solution, because we're going to get sodium and chloride building up. But we also want to know what the nutrient levels are, so that we can avoid having the need to have a very high discharge or regular dumping of the solution. If we were in a nursery or a greenhouse, we could say, well, we can blend some of our water, perhaps if we're capturing rainfall. For some growers, indoor growers, that might be an option, but for the most part, we're relying on purification with a reverse osmosis system, and we'll come back to RO later on. But let's just focus on this increasing of drainage or waste percentage in terms of managing the content of our reservoir, and also how much of that nitrogen, phosphorus, and is going into the environment as discharge or waste. So if we have a very simple system of drain to waste, then it's straightforward. We're less sensitive in our system to the incoming water quality, because we're just discharging any unused nutrients and ions into the environment. So if we look at this graph, we've got our source water. It might have some level of treatment. We have a starting fertilizer formulation. We may be correcting pH up or down, often with, could be nitric acid, phosphoric acid, sulfuric acid for dropping pH, perhaps citric acid, and for pH up, we might be using a potassium-based salt. And then we've got plant uptake, and we've got our root solution, and then we're getting drainage through it, and we're getting discharge of our leachate into the environment. And one of the challenges is here, this is simple to manage, but it's most wasteful. And for many indoor growers, we're not in a situation where we can reuse that discharge on other less sensitive crops, and hopefully it's not going down the drain in your environment. Now, when we have a recirculating or closed system, the situation is a lot more sensitive to the incoming water quality. So we just go through some of the components in this system, we can see that the root solution in our reservoir is going to change over time, and we need to really think about how we're managing these different components. So we have our source water, some level of treatment going in, perhaps there's some filtration, there might be an RO system here to purify it, perhaps dechlorination to remove chlorine. We have a starting fertilizer formulation that's going into our reservoir, and then our makeup fertilizer as EC level goes down over time as plants take up the nutrients may or may not be the same as our starting fertilizer. But the bottom line is, if we wanted to optimize our system, we would be smart about it. We would start off with a certain balance of nutrients from a starting fertilizer, and then we would adjust the ions that are being taken out most quickly by the plants or are changing because of these components in the system. So our makeup fertilizer may very well be different from the starting fertilizer if we're trying to maintain nutrient levels in the root solution. For example, if we think about plant uptake, ions such as nitrogen, phosphorus, potassium are going to be taken up more quickly than calcium in the system. The pH correction material that we use is going to add some ions into the system. For example, if it's nitric acid, it's going to be adding nitrogen. If it's phosphoric acid, phosphorus, and so on. Most of those pH up products are going to add potassium. Plant uptake, as I mentioned, you're going to have selective uptake of nutrients. If we think about the treatment system that we have, then many of our treatment systems are also going to change that nutrient solution. So for example, if we have an ozone system, it's very likely that micronutrient chelates such as iron chelate is going to be broken down as we pass that water through ozonation or UV radiation and so on. We have to supplement back micronutrients. So if we're going to recirculate and avoid dumping of our nutrient solution on a regular basis, then we want to have high water quality coming in, but we also want to be monitoring the nutrient level over time and considering how we're influencing those nutrient levels in terms of all of these factors so that we can supplement back a makeup fertilizer that is really trying to just add in the components that are changing over time in our solution. So we change now from our chemical water quality in terms of the ions. Let's talk now about chlorination. So if we've got a municipal supply, it's very likely in the US that we're having chlorine added to control bacteria in our piping system. And the challenge is that if you've got, for example, 2 parts per million of chlorine coming in from your municipal supply, that's high enough in a hydroponics system to cause phytotoxicity on plant roots. So the top image there is from Genovese basil. We do a lot of phytotoxicity trials with different water treatment chemicals. And if we have plants growing in containers, such as these basil plants, then what we see is with a sanitizing chemical, generally root systems are quite resilient because a lot of the active ingredient of those chemical treatments gets used up or deactivated by the growing media, for example, peat or bark that's in the substrate. And in that container growing situation, our foliar applications are going to be the most likely source of phytotoxicity. However, in hydroponics, where our roots are bathed in a nutrient solution, we don't have the organic matter to eat up the active ingredient from chlorine or another sanitizing chemical. And this image is from my colleague, Dr. Rosa Raudalius. She's doing a lot of great work on biofilm management and root diseases in hydroponics. And what we're looking at here is 3 different levels of free chlorine, which means it would be HOCl. It hasn't reacted, hypochlorous acid has not reacted and formed any combined chlorine. So if we've got 0.5 or 1 parts per million of free chlorine, we can see a major impact of that fairly low free chlorine level on root growth and yield of hydroponic lettuce, for example. So dechlorination is an important step when we've got a municipal water supply in hydroponics. We've done quite a bit of work with granular activated carbon filters. It's not the only dechlorination technology, but it's a very simple one. And what we've got here is a media filter like we would use for a sand filter, but instead of having silica, sand, or crushed glass in that filter, we fill it with a carbon source that could be coming from bituminous coal or from coconut coir or some other source. And it's very effective at dechlorination. And so what will happen is that chlorine, in the case of chlorine, will oxidize and it'll become Cl- chloride when it's passed through a GAC, granular activated carbon filter. And those filters are very easy to manage. But be aware that granular activated carbon doesn't just remove chlorine. That can be good and it can be bad. So what we're looking at here in this table is we're looking at different contact times where we are passing our irrigation water through a carbon filter, and it's got different amounts of time before that drop of water in our line enters and then exits the filter, between 0 and 64 seconds in the research trials that were done by one of my graduate students, George Grant. And if we look at free chlorine levels, then we can see it's very rapidly taken out by the carbon filter. It's changing chlorine into chloride, just a salt. If we look at total chlorine, which includes free and combined chlorine forms, GAC is also very effective. But if we think about one of our fertilizer salts, such as iron chelates here, iron EDDHA, then one of the challenges is that a GAC filter will also remove a level of other organic molecules, such as iron EDDHA. That's not going to be an issue for the incoming water source, but if you put a GAC filter into a recirculating system and our nutrient solution passes through that GAC filter, it's very likely to remove some of our fertilizer micronutrients. Okay, so we would need to supplement back in with our iron chelates. And we were looking at fertilizer dyes as well, that you'll sometimes have the blue dye that's added into fertilizer. It's another organic compound. As you can see on the right side of the screen there, as the amount of contact time with a GAC filter increases, it'll take out these other organic materials. Now, usually for both our production system and for our water sources used in indoor production, we don't have pesticide residues that we need to remove. But just to point out, if you've got, for example, a greenhouse or nursery where you've got a surface water source that perhaps is getting herbicides from surrounding area, then GAC filters are very effective at removing those other organic pesticides. So here we've got insecticides, herbicides, plant growth regulators, and sanitizers that we've tested in my lab here, and all of those are removed at a high level by a GAC filter. So if for some reason you had some type of a pesticide product within your system, or there was some contamination of your water source, a granular activated carbon filter is a good choice. Okay, let's move now to the last issue. It's not the only issue, these ones that I'm covering, but the last issue I'll talk about in terms of the water source, and that is bacteria that can be a source of inoculum for biofilm. And so here we've got an image from Dr. Peter Conjoyan up in Connecticut, and he did a lot of work on biofilm a few years ago. And he has his own greenhouse operation. And when he dug into the pipes, what we're looking at here is that even though he had a municipal water supply, there's biofilm there present inside those pipes, especially if we add a nutrient source from our fertilizer, we're likely to get a lot more algae and biofilm forming. And then on well water side, I'll sometimes run into issues that I'm helping growers with in terms of especially iron or manganese or sometimes sulfur bacteria. And this is where we have bacteria that are getting some of their energy source from the ions dissolved in the irrigation water. And so we're seeing this clogging of a screen filter here from iron bacteria, and this is coming straight from the well. So sometimes we run into issues where our water source, even though we've got a fairly pure source of municipal supply of well water, that we need to quantify bacteria levels and to treat for it. And here we're looking at, on the right, there is a technology called Petri films from the 3M Corporation. We use them a lot. And there are different types of Petri films. These are very suitable for on-site measuring of bacteria counts. And so here we're using a heterotrophic or aerobic bacteria count here. This is very feasible, especially for this particular test, where you take a milliliter of water sample, you can dilute it out with sterilized water. Here it's at 1 to 100. Put that drop onto this, it looks like a yellow sticky card that you'd use for testing insects. You put that into a drawer for 3 days and then count the number of dots, which represent colony forming units or CFUs. And there are also Petri films available for fungi and for food safety pathogens such as E. coli. And what we do is we use these, when it comes to bacteria and biofilm specifically, we use these as indicators of where we're seeing bacteria coming into our production system and whether we're seeing a drop after whatever treatment system that we're putting in place. And this is in a greenhouse operation, and you can see that the well water, this is the operation that had high iron bacteria, has already got a very high level of, in 1 milliliter, 1 cubic centimeter of water, 48,300 colony forming units of bacteria. And by the time that water had traveled through the irrigation line to an emitter out in the greenhouse, it's up over 2 million colony forming units for every milliliter of water. And the difference from the well to the dripper is the biofilm in the irrigation line. And in this case, we know that even though it's well water, not pond water or some other surface source, we're already getting a high bacteria count in the water that's coming in. So we need to treat at the source. And specifically for iron or manganese or sulfur bacteria, then our most common types of treatment would be to add in an oxidizing chemical treatment such as ozone or hydrogen peroxide or potassium permanganate or chlorine. And then we allow a certain period of contact time depending on the chemical, for example, 2 minutes with chlorine in the piping or into a holding tank, followed by sand filtration to remove any killed bacteria and perhaps oxidized iron, rust essentially that's formed from our oxidation, and then removal of harmful residuals. If we're using a chemical like chlorine, for example, we might put a GAC filter after this treatment. And there's an alternative approach here as well, which would be a point treatment with a technology such as ultraviolet UV radiation to kill the bacteria at the source. The only way we would know that we were getting those bacteria at the source as opposed to some other part of our system is by doing some testing. And what we're seeing here in the images, we're seeing the backflushed water in the bottle at the top right. We've got sodium hypochlorite bleach being injected as our oxidant in the tank, followed by sand filters in parallel with automatic backflushing. And then we're seeing Petri films here with very high colony forming units per mil bacteria count at the wellhead, but we're seeing after chlorination that we've managed to control the bacteria and reduce this as a source of inoculum for biofilm. And in that particular grower location, the biofilm was causing clogging of drippers and loss of crops. So what is biofilm? Well, it's a complex of microorganisms and also snotty slime that those microorganisms produce, whether they're proteins or polysaccharides. And the source of inoculum within our irrigation line is typically going to be waterborne microbes that attach to the sides of our PVC lines and so on. They grow, and then at some point they mature to the level of detaching and causing infection or an inoculum to flow through to other parts of our irrigation system. And it can be a problem for several reasons. You know, biofilm and algae in our indoor areas can cause clogging of emitters. It can encourage pest levels such as fungus gnats, which attack the roots of our plants. It's an aesthetic issue. Algae on the floors can be a worker safety issue. And potentially these biofilms are not just bacteria and fungi that are beneficial or benign, but it can also include pathogens in terms of plant pathogens or food safety pathogens. But it's important to realize that when we're controlling biofilm within our irrigation system, sterility is not the goal. And nature abhors a vacuum, and if we sterilize everything, we're creating an environment where it's much easier for a plant pathogen to get established and infect our crop. And here's an example of research work in that area where these researchers looked at rock wool and reusing rock wool, which is not a normally recommended strategy, but they were wanting to test whether the indigenous microflora, the biofilm that was forming in the rock wool, whether that would have a negative or a positive effect on a subsequent crop if they reused the rock wool. So they went through a series of trials and with cucumbers grown in rock wool. And what they found was that if they planted crops into rock wool that was not sterilized and did not come from a crop that had Pythium, and now they inoculated with Pythium aphanodermatum, that these non-sterile rock wool cubes would actually result in less infection than starting with heat sterilized used rock wool. Okay, so there was some level of suppression of infection by the biofilm that was present in the rock wool. However, it's not a great idea to reuse growing media. And if they reused rock wool from a cucumber crop that had previously had Pythium, and they reused that rock wool, then they would get a high disease incidence in the next crop. So sterility is not the goal within our system, and there can be some suppression from the naturally forming microflora, but we do need to be careful not to be transferring pathogen spores from a previous crop into the subsequent crop. Now, I don't work a lot with beneficial microbes, but there is a lot of research work in this area. And one of the great things about indoor production is if beneficial microbes are going to have a chance of being really effective, it's exactly in this environment, because we often don't have a lot of naturally forming microbes from compost and so on as an input source. And we can optimize our environment for not only our crop, but also our beneficial microbes to be effective. And there is lots of work that is shown that beneficial microbes within hydroponics can be very effective in terms of disease suppression. And again, I'm not a plant pathologist, but it was explained to me very well in a recent workshop that I was at by our plant pathologist, Carrie Harriman, who runs our diagnostic lab. And she described it this way: is if you think about a bar, a pub, and you've got a whole bunch of beneficial microbes that are taking up space, using resources, then if we introduce into that system a zoospore, then we're going to get a lot less infection than we would if that bar is empty. And there is no competition. There are no disease-suppressing compounds being released by these microbes. So basically, if we've got a healthy microbial community in our hydroponic system, then it's actually helping us in terms of disease suppression. Now, when I was doing work with this Clean Water 3 group, which is a bunch of people working on recirculating irrigation in greenhouses and nurseries, one of my colleagues, Jennifer Park in Oregon State University, was looking at HACCP analysis and looking at where do we have hazards and critical control points for the Phytophthora ramorum pathogen that causes sudden oak death. And we can take a similar approach when we're thinking about the sources of inoculum and their management for biofilm and pathogens in indoor production. So we have a number of inputs that are coming into our system, and we want to think about the risk of those inputs in terms of being a source of inoculum. So equipment and surfaces that have not been cleaned between crops, root substrate that is being reused. If we're using a root substrate such as peat, peat has a lot of great characteristics to it, but if that peat has been stored in a way where we've had fungus gnats have been allowed to establish, we may have algae spores already in our peat, that's going to be a source of inoculum. Our source water, as we showed there with the iron bacteria, that could be a source of biofilm organisms. Young plants, that's an absolutely common, very, very important source of plant pathogens being introduced into our indoor production system to start with. The fertilizer is unlikely to be a source of biofilm or pathogens, especially if it's a mineral fertilizer. But when we do trials and we try to encourage biofilm to form in our irrigation lines, we use an organic fertilizer that has not only got mineral nutrients such as nitrogen and phosphorus, but it also contains a carbon source. So if we are using an organic, in quotes, material, then we're absolutely encouraging biofilm growth in our system. Same thing can happen if you're introducing in, for example, humic acids, citric acid as well. Then we've got our recirculating system in here with both our crop plants and our reservoir, and we may be treating within that loop, but if we're not controlling for inoculum coming in from other sources, we don't have complete control. Airborne spores, whether you need a HEPA filter within your system to remove spores such as botrytis, I think is a very interesting area of research right now. And then also on the hands and feet and so on of your workforce are all sources of inoculum. So I think a systems approach to figuring out where is inoculum coming from is critical in terms of trying to get an overall management of biofilm within your system. And it also fits with the GAP approach for managing irrigation water. And if you look at the National Good Organic Practices Program, it very much specifies this type of HACCP analysis, mapping water flow and potential contamination points, figuring out where you need to have treatment and where is risk coming from, avoiding applying water to foliage in terms of, for example, E. coli contamination. Having regular testing for E. coli, salmonella, and other types of food safety pathogens. And then treating water and testing for residual sanitizing agent on produce. And we'll talk about residuals in a moment. So basically a systems analysis is needed. But what we can do now is kind of move on and say, okay, well, we need to understand the system, but let's look at some specific treatment technologies. So the basic steps we're going to go through in terms of biofilm management are going to be to clean or sanitize first, then disinfect between crops, and suppress buildup. So the images that we've got in the right-hand side, this is a hydroponic potted herb production facility in Denmark that I visited. And what they were doing is in their recirculating nutrient solution during the crop, then they weren't actually doing any treatment. But what they were focusing on was a very high level of cleanliness, sanitation, and in the top you can see there are gutters that are being put into a steaming room where they are sterilizing between crops and always starting clean. So let's go through some of those options there. When it comes to surface sanitation, unfortunately, there's just not a lot of research work on all of the different pathogens that we have. Warren Copes at USDA ARS is one of our few plant pathologists who's really looked at surface sanitation. And depending on the pathogen of interest, in this case it's Botrytis cinerea, then and also the life stage even of that pathogen, we've got different levels of sanitizers that need to be applied. But I'll just go through a couple of things, a couple of points in this table here. So here we've got 4 different sanitizers as examples. And in this case, there was a metal surface, galvanized metal, that was inoculated with Botrytis spores. And then the researcher was looking at what concentration was required to kill 90% of that inoculant. And we've got xylitol, which is a mix of hydrogen peroxide and peroxyacetic acid. We've got off-the-shelf kind of chemical grade hydrogen peroxide alone. Green Shield, which is an example of a commercially available quaternary ammonium chloride product, a surfactant. And then bleach, a chloride bleach, sodium hypochlorite. And so there are different types of chlorine, but it's going to release hypochlorous acid into our irrigation line as our active ingredient here. And I'll just point out that our dilution level varies hugely between the different sanitizers that we apply, and we need to make sure that we're using something that is registered for use and safe for our workers, as well as being effective. And sometimes growers will cut corners. And so, for example, if we just compare xylitol, a commercial product with an EPA label, with hydrogen peroxide, you can see that hydrogen peroxide alone required a much, much higher concentration to control botrytis than xylitol. And in addition, for surface sanitation, you'd have to check with your regulators whether that was actually a legal application. If we think about bleach, a very common recommendation is a 1 to 10 dilution of bleach. That's a lot of bleach, especially to use in a confined space. And hopefully your workforce is using respirators and protective gear to apply that. Another point from Dr. Copes' work was that it all depends on the surfaces that we're trying to sanitize as to how effective these sanitizing agents are. Basically, avoid porous surfaces. And so as we go from the top to the bottom, if we've got wood, which I doubt very much that most of your indoor production areas have got any wood in them, but there may be some other porous materials such as fabric in there that will be very hard to clean and sanitize compared with non-porous surfaces. If we're looking at specifically irrigation lines and disinfection of those, then the most common strategy that people will use is to choose one of the following chemicals. So there are surface and line cleaning products, which are typically a combination of an acid and a surfactant. For example, Strip It is a product that's commonly used. There are various quaternary ammonium chloride products. So these are surfactants. For example, Green Shield or Clean Grow would be a couple of examples. Chlorine dioxide is an oxidant that's sometimes, it's a very strong oxidant. It's actually stronger than hypochlorous acid or what we typically call chlorine. And those are typically done as overnight treatments. And also hydrogen peroxide or peroxyacetic acid or products such as xeritol. And so follow the label requirements for these products and basically blow out these lines first, then apply one of these chemical materials, and then rinse and remove any harmful residues before you start your next crop. And again, we've got enclosed spaces, and we also often disposal of waste chemical in indoor operations can really be a major issue. Now, if we think about all of the different sanitizing agents or disinfectants, water treatments that we've got available, it can be a little bewildering. But one of many ways to categorize those is whether they are slow-acting, long-term residual materials, or if they're highly reactive materials that are may even just be a point treatment at one point in your irrigation system. So when we're looking at controls for irrigation lines, we've got an existing biofilm problem. We're trying to treat and have a cleanup through the entire irrigation line. Then we need a chemical that has some residual activity. And so some of the products that are in the middle of this table, chlorine dioxide, chlorine, quaternary ammonium chloride, peroxyacetic acid, these are all products that will travel, you inject it, it'll travel through your irrigation line. However, all of those products can potentially have problems of phytotoxicity if they were then applied in a hydroponic system. Okay. Then we've got some very slow acting materials, such as copper ionization, which is metal that is electrolyzed and put in solution, or chloramines, which are combined chlorine, where a chlorine source has been added in to a fertilizer solution with some ammonium. And then down the bottom of this table, we've got our very reactive materials, such as ozone, or our point treatments that have no residual activity, such as ultraviolet light, heat, and filtration. And we may use some of these residual materials to clean up our system between crops, but when we're talking about biofilm management within crop cycles, then we're talking about highly reactive or point treatments. And so we've done a lot of work with managing biofilm and irrigation lines. And what we see is that if you have an existing biofilm problem within your irrigation system, you can add a low level of some sanitizer or a point treatment for as long as you like, and the biofilm will not go away. You have to shock the system to get rid of that biofilm and start clean. And if you've got a low level of inoculum on the water source coming in, or you've treated for bacteria in that water source, then often a shock treatment between crops, cleaning up between crops, but not having any residual treatment is adequate as we go through a crop cycle. And if we want to put in a continuous application of a chemical into our irrigation lines, then it's somewhat effective for suppressing biofilm, but when we are adding enough of any chemical to really suppress biofilm, we have a phytotoxicity risk in hydroponics. And the other point that we see is if we want to compare the biofilm levels with clear water or a nutrient solution, then anytime we're adding nutrients into our irrigation system, then we've created this wonderful environment for growth, not only of our crops, but also for biofilm. And you might have noticed that what we'll do when we're doing these biofilm tests is we add in an organic fertilizer, as I mentioned, that's got nutrients as well as a carbon source, and biofilm organisms, bacteria and algae, just love it. It's sugar to them. We also do some biofilm trials specifically in hydroponics. And so here's one of the trials, for example, with aerated bucket system with growing lettuce. And what we're looking at in this graph is we are looking at different sanitizers compared with a control, no treatment, in hydroponics in these aerated buckets. And the vertical axis is turbidity, okay, which is lack of clarity. It's the amount of particles and algae in the solution. And sure enough, we add in a chemical into our irrigation system, into our nutrient solution. Yes, we can significantly improve clarity and control algae and particles and bacteria in the water. However, the problem is phytotoxicity. And so here we're looking at on the left at an untreated control lettuce plant, and on the right, the damage that we have here to the root system is from a hydrogen peroxide, peroxyacetic acid product, in this case xylitol, being applied at a 1 to 2,000 dilution, which is not a very strong concentration, and it causes a high level of phytotoxicity. So the point is that roots are very sensitive to chemicals in hydroponic culture, okay? And so if you look at a quaternary ammonium chloride product, a surfactant, then levels below a part per million can sometimes cause phytotoxicity. If you look at a hydrogen peroxide-based product, then even down as low as 8 parts per million can cause phytotoxicity. And also, as we saw earlier with Rosa Raudalis's work, plants are very, very sensitive to free chlorine. Okay, so what we need to do then in terms of our treatments are first have a pre-filter to remove particles to reduce the sanitizing demand. There are a bunch of different types of filters that we test in irrigation systems, but the most common and suitable ones for indoor production would be a disc filter, which is, you can see it's a combination of these stacked discs, which can be automatically backflushed. A screen filter, again, this is an automatic cleaning filter, or sometimes a cartridge or a sock or a bag filter. And the problem with these filters, even though they have very fine pore sizes, is there's a lot of labor. They clog very quickly and need to be cleaned or replaced. Sometimes growers will use a sand filter, even in indoor production. This is not really the ideal type of filter, even though it's the most common used in nurseries. And the reason is it takes a lot of nutrient solution to backflush to wash out the sand grains. Okay, so after we have some pre-filtration, and you're going to see with all of these treatment options I'm talking about, they're all sensitive to turbidity or particles in the water. They need pre-filtration. So ozone is one of these options because it breaks down just to oxygen. It is expensive. It is the most complex of the treatment systems that we have to manage. And it's strong enough to actually break down the chelates, such as iron chelate, and you may need to supplement back in with more iron chelate if you're using this in a recirculating system. With membrane filtration, one of the challenges is flow rate. And we have different sized pores in membranes. We've got reverse osmosis, which is so fine a pore size that it'll actually take out ions and nutrients. So we would have to supplement that fertilizer back in. We also have an issue of brine disposal. So when we pass water through a membrane filter at high pressure, we're left with a very high salt solution. And for indoor growing, especially if you're in an urban environment, then that brine cannot be legally poured down the drain. So flow rate is a problem when we've got membrane filtration, but it's an option. I don't have personal experience with using heat, but it's more commonly used in Europe. And so basically you pass your water through a series of heat exchangers to raise it up to somewhere around 40 to 95 degrees Celsius for a few minutes, and then go through back and recapture that heat before the water is recirculated. And then UV radiation is also another point treatment, but it's very dependent on having low turbidity, good pre-filtration, so the light will penetrate and kill target microorganisms. And again, UV can break down micronutrients. So in summary with all of this is there are a lot of water treatment technologies out there. We can use chemical treatments when we're cleaning and sanitizing between crops, but we really want to favor some of these point treatments when we're recirculating nutrient solutions inside the crop. And I get every month or so, there'll be a new technology. It sounds amazing. It's the silver bullet. But I would just say, don't be the first adopter of a new technology when it comes to water treatment or biofilm management, because this is all about risk management and you want to be conservative. You don't want to solve one problem and create another. So take-home messages are incoming water quality. It affects nutrient balance. If you monitor, think about how the different components are taking up nutrients and changing the nutrient solution, then we can have a smart way of supplementing makeup fertilizer and reduce the amount of dumping. We want to clean and disinfect between crops. And if we're treating within our recirculating system, we want to have a point treatment that's not going to add any harmful residuals. And with that, I'll just mention a couple of resources. There's a website that I manage called Clean Water 3 that's got a lot of information in it on water treatment, different technologies. And then we run some online extension courses. They're 4 weeks long. They're all in English and Spanish. We get about 100 growers in the US and overseas in each course. And we've got several of these courses that we're offering this year that are relevant on this topic. So with that, Cherry, I'll take any questions.